would happen if you dropped a bowling ball and a feather and air resistance was not a factor. Okay? So, this video, if it still works, yep. They actually did this. So, you can cut off the lights. We're going to watch this. It is so cool.
This is NASA's Space Power Facility in Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in conditions of outer space, and it does that by pumping out 30 tons of air in this chamber until there are about 2 grams left. And it's got an eccentric construction as part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, strongest material to build a vacuum chamber out of, so they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber. Drop 2 millitour in the last 30 minutes. But once it's complete, there's a near perfect vacuum inside. 6104 manual, 10% older. Station 1, go for drop. TCE 30-1, pressure set point at 240 psi. We are go for drop. 10, 9, 8, 7, 6, 5, 4, number 5, 2, 1, release.
How feathers are staying like in the exact same position.
Look at that. They came down exactly the same. Wow. Exactly the same. Exactly the same. Those don't move, nothing. Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the earth. So he concluded they weren't.
So,
there's no gravity.
Well, there's gravity, but there is not air resistance. So they have sucked all the air out, so the objects still fall because they're still on Earth. But there's, there's like little tiny particles in the air that we're like breathing in and everything. And so that is what's like pushing up against. But whenever all of that is taken out, it's just like empty space, like you would be out in outer space. And then there's no air resistance. So when that feather is falling, those little tiny particles of air that are normally there are not there, so they're not like pushing up against it. And so the feather just falls like the bowling ball. So this could only happen like in outer space or in this crazy vacuum chamber that they have created there, which is kind of cool. So it's also kind of cool that they went through all of that just to drop a bowling ball and a feather because they obviously use that for testing. Like, you could see how it had that great big door. You don't need that great big door to put a bowling ball and a feather in there, but they had that great big door because they like put pieces of like things they're going to send to outer space in there to test them to make sure that I guess they can hold up in that sort of environment. So yeah. So anyway, I thought that video was really cool. And it's not something that you can see happening because our environment is always going to have air in it. Wherever we're at, there's going to be air, because if there's not, we will be dead, right? So unless you are somewhere, like if you were to go into that chamber, you would need like a full space suit, like the ones that astronauts wear whenever they go out into outer space, to fix things on the spaceship and stuff. So, yeah, so it is unlikely, unless any of you become an astronaut, which is super hard to do, that any of us will ever be in a zero gravity or zero air vacuum environment like that. You're right. You can also just, these days, you can also just be super rich, and they can send you up in a spaceship. Beat cancer. Yeah, Steve Jobs died of pancreatic cancer. Huh? Very, very, very few people ever beat pancreatic cancer. So, yeah, I'm not saying that you don't have a little better chance if you have lots of money and can explore all of the options for treatment, but being rich is not everything. Okay, so we're going to walk through this together and kind of explore these equations that we are going to be using. So, about 400 years ago, Galileo Galilei, which is like the Galileo that you hear of in science class, who also was an astronomer and did a lot of different things, discovered that gravity exerts a force on any free-falling object so that the distance fallen will be related to time by this function. D equals 16t squared. Now, there are several things to note about this equation. This equation ignores air resistance. So it is only applicable for dense objects with little air resistance. As I just said, we're not going to be in a no air resistance situation ever, probably, in our lives. And neither was Galileo. The technology to have a vacuum like that was not available. But if you drop something that is a dense object, it's not got a lot of air resistance. So if I drop something like the ink pen or the paper clip that I dropped yesterday, they don't have a lot of air resistance, so it's going to be pretty close to following Galileo's equation. If I drop something like a feather or the piece of paper, then it's not even going to be close because there's so much air resistance that, that's going to float down to the ground very slowly. Also, this equation only applies on Earth. Other planets or the moon or other places that you may go are going to have different gravity. Okay? If you go to a bigger planet, it has more gravity. If you go to a smaller planet or a moon or the moon, it has less gravity. So, like if you were to go to the moon, this number right here would be smaller because the gravity would be less. And if you were to go to Jupiter, then the number here would be larger. So this only applies on Earth. Once again, probably none of us are going to have to worry about applying this outside of Earth in our lifetimes. But so this equation only applies when distance is measured in feet and time is measured in seconds. You can make the same type of equation with, like, the most common to use, particularly in science, is meters per second. We usually use the metric system. So it would just change the numbers that you would see here if you did that. You could even change it to be like miles per hour or a lot of different things. But we're just going to stick with like one version of this equation with feet and seconds because feet is what we're most used to dealing with in regular life. So when we see the answers, we can kind of relate to what they mean there. All right. Imagine a student drops a pumpkin from a building that is 100 feet tall. Okay? So we are going to ignore air resistance because a pumpkin is a relatively dense object that is not going to have a lot of air resistance. Okay? So what we want to find using Galileo's equation, which was that the distance equals 16 times the time squared, we want to figure out how far the pumpkin's going to drop in this amount of time. Okay? So at time 0, the pumpkin has not felt any at all because it has not been dropped yet. And how high is it above the ground? 100 feet. So it is 100 feet above the ground. Is it related to this? Quickly. I can do some calculus and tell you how fast it'll be going, but I'm not going to do it right this moment. Okay, let's get our equation first and I'll tell you. All right, so the distance fallen, so after 0.5 seconds, and we're going to use our calculator on this, so if you don't have your calculator, I'll just do the calculations up here. You don't have to go grab it just yet. All right, so make room for my calculator over here. So if I use this equation, if I do 16 times 0.5 squared, in the first half a second, the pumpkin will drop 4 feet. Okay? So how high is the pumpkin above the ground now? 96 feet. Okay? Because we dropped 4, so now we're only 96 feet above the ground. All right, if I plug in 16 times 1 squared, it's just going to be 16. This is the total distance fallen, not like 16 more feet, but total since it started dropping. Okay? So how high would the pumpkin be now? 84. It is the total amount dropped, not like 16 more feet past this. So it's 16 feet since it was dropped in the beginning. So we do 100 minus 16, not the 96 minus 16 for that. Then if we do 1.5, 16 times 1.5 squared is going to give us 36. So that means 100 minus 36 will give us 64 over here. 16 times 2 squared is going to be 64. So 100 minus 64 would give us 36. 16 times 2.5 squared is going to give me 100. Okay, how high above the ground is it at 2.5 seconds? 0. Now, I could keep going with this equation. If I do 16 times 3 squared, I get 144. But over here, I'd get like negative 44. Is this making sense anymore? It would, but knowing what we know about the ground, right? The ground is going to stop the pumpkin, right? So it might make a little bit of a dent, but it's not going to go real far. If you were dropping this into like a well or something where it was going down into a hole, then we could still apply this, because 0 would be like ground level and then it would be dropping down below that. But if we're just hitting the ground, what we would know is like we really can't apply this past that point, right? So even though the equations tell us something doesn't mean it's going to actually happen in real life for that. So I want to write an equation that will give the height of the pumpkin after t seconds. So write the equation of this pumpkin. So h of t is what we'll call it. And I need the equation that will give me the height of the pumpkin. So that's basically this column over here. And I need its variable to be a t.
What do you mean the variable?
So, like, for example, let me just give you something kind of wild that's not going to work. I could do, like, 80 minus 5t. This is not going to work. It's not related to anything that we were just doing. But if I did 80 minus 5t, I could see, like, in fact, we haven't really done these on these calculators, but if I do 80 minus 5x, and I go over here to the table, table set. All right, so, like, it gives me these numbers, which that's not the numbers that I want. That's not 196, 84, 64. So, like, what equation could I use? Think about, like, what we were doing to get these numbers over here that would give me the height of the pumpkin. What do you think, Evan?
100 minus 16t.
Okay, so 100 minus 16t. All right. I'm going to put this in the y equals on this calculator. I know we haven't really done this on the calculator. Don't worry too much about doing this. Yeah, Desmos can do the same thing. Yeah. So if I do what Evan told me, I don't get the right numbers. Because we weren't doing 16 times t, we were doing 16 times t squared, right? And then what we were doing with that is we were taking that away from the 100 that we started with, right? So if I go over here and make it squared, then my table will give me those numbers that we were looking at. So this would be our equation, because we started from 100 and then we subtracted that gravity piece, right? That piece that told us how far it fell due to gravity. Now, if you want to know how fast the pumpkin is going when it hits the ground, just side note, you would take the first derivative, which would be negative 32t, and then you know it hits the ground at 2.5 seconds, so you would plug in 2.5, so negative 32, negative 32 times 2.5 would be, it's going to be negative 80 feet per second. It's negative because it's decreasing, so it's going down. So 80 feet per second is how fast the pumpkin's going to be going whenever it hits the ground. So 80 feet per second, let's just convert it. Feet per second to miles per hour. Let's see, I'm going to do 80 feet per second. So it's going about 55 miles an hour when it hits the ground.
Depends on how soft the pumpkin.
I think it's going to, yeah, it will depend on how soft the pumpkin is. If it's a bowling ball, it's not going to look good. And where you get hit, if it hits your toe, I think you're going to make it. In the head, we would not want to try, right?
It's like borderline. It's like rotting almost dead.
We would not want to try. So, that's a little calculus for you, some magic of calculus, but of course you don't have to know how to do that. I was just wanting to see if I could use a little calculus to partially answer Caitlin's question. All right. Yeah. Yeah, I should. Yeah. I think I did. I did have him do that problem, but I can't remember it now. I've forgotten it. All right, so let's talk about this. Suppose that the pumpkin is dropped from 75 feet instead of 100 feet. What would the equation look like then? What would our H of T equation look like then?
75 minus 60 squared.
Okay, the gravity piece right here, this minus 16t squared, it stays the same. But this number right here we're starting from would change to 75. Okay, so these equations can be used to find like how long it'll take if you drop something to the ground. But there's another aspect that we can talk about. This is talking about just dropping something, right? So gravity is doing all of the work. Now there's a chance that you don't drop something. You might take the pumpkin and you might throw it up into the air. Or you might throw it down with like a force, like if you're trying to hit somebody, right? Oh wait, no, we got to do this problem before we talk about that. Okay, so let's do a different problem. So a flower pot is dropped from a windowsill in a 5th floor apartment. The window is 43 feet above the ground. So I want to write an equation that will give the height of the flower pot. All right, so H of T, 43 minus 16t squared. This particular flower pot is still on Earth. We're ignoring air resistance, and we're using feet and seconds. So, no, not, that would make it a lot harder. Like even when we do calculus problems, we still ignore air resistance. So if you become a physicist or something, if you major in physics in college, you will learn how to factor in your air resistance. But it makes the problem so much harder. Yeah. So we have to ignore air resistance for this. How long will it take the pot to hit the ground? How can we figure that out? Okay, we could plug something in somewhere. How high is the flower pot when it hits the ground? Its height is 0, right? So this right here stands for height. So we could put a 0 right there. Okay? So, if I want to solve this for my t, Aiden, what would I do to solve that for t? Very good. Okay, so now I've got negative 43 equals negative 16t squared. What would I do next? Good. We'll divide by that negative 16. We're going to use our calculator for this because this is definitely not something that's going to come out nice. And we will get 2.6875. Okay, what's the last thing we do? Square root. A lot of times we'll put a plus or minus with our square root, but in this particular case, does it really make sense to have a negative time for this one? It does not. So we're just going to go with t equals 1.639 seconds. So if you are standing below this flower pot, you have 1.639 seconds to move before. You probably got it. Well, it's not much considering that most people have like at least a second reaction time. So I think you could. Yeah. Yeah. So it's a little tricky. All right, don't pack up yet. We got a couple more things. All right. Okay. We're gonna do this one more problem. Okay. All right, example 3. A dense object is dropped from the top of a tall building. It takes 4.2 seconds to hit the ground. How tall is the building? So this is a pretty cool application because you can, if you're ever somewhere really high, if you drop something and see how long it will take to hit the ground. Now, I would not suggest this if there are people below, but let's say you're on a bridge and there's nothing below you. Yeah, I think so. Or really any really tall building, but yeah. Yeah, don't. It can, yeah. It's going to be going real fast by the time it hits the ground. All right, so. I don't know if that's true or not. I mean, maybe not kill you, but it's going to be going pretty fast. The other thing is that you can't, like, totally ignore air resistance on that because it is such a long distance. The air resistance is probably going to come into play. You hit terminal velocity, which we need to talk about tomorrow, but we don't have time for that right now. Terminal velocity is also cool. All right, so let's talk about this. So just dropping to hit the ground. Okay. So our equation h of t equals. I don't know how tall this building is, right? Okay. So I'm gonna put a question mark right here. I don't know how tall it is, but I know that I would have minus 16t squared because of gravity, right? So question mark minus 16t squared. How high is the object going to be when it hits the ground? 0. So I'm going to go over here where my h of t is, and I'm going to put a 0 right here. Okay? What else do I know that I can plug in? All right. Where would I put that 4.2? For my time. So I've got 0 equals question mark. Okay? So 16 times 4.2 squared. I'm going to put the there. So I'll get 0 equals question mark minus 282.24. And then if I want to solve this, I just got to move that over to the other side, right? 282.24. So that height of the building, the question mark, is just going to be 282.24 feet. So you could do this if you were like on a really tall bridge. You could drop it, see how long it takes, you know, like a little rock to hit the ground. Yeah, it's really hard to do unless you're pretty high because it's hard to time it. Okay. All right. There was supposed to be an assignment tonight, but we didn't get quite far enough, so we'll move it to tomorrow. Does he have a 4th period class? Does he have one at Surrey, maybe? I can't because I don't have him anymore.
It's Wednesday. It's Tuesday, Thursday. So why would you just go both?
Well, does he have any class on Wednesday? Maybe he doesn't have a class. He probably doesn't have a class if he has a Tuesday, Thursday Surrey class.
Can we get a 2-point card on that list?
I don't know if I'll look
4 out of 6 is better than 2, and I'll happily take that 4 out of 6 and a 2 out of 6.
Oh, that's not a 2-point curve. That's a big point curve.
2 point will be 4 out of 6.
Right. But it will be out of 100 in the end, so they're like 8 points apiece. That'd be like
Hey,
a
what's
16
a 2 out of 6?
curve.
Like, what would that grade be?
Failing.
2 out of 6 is a third, which is 33.3.
So let's.
They'll go together though.
I feel both of them.
The
So.
2 parts will go together.